Hello, everybody. So I'm going to try to remember to look at the camera. That'll probably feel more natural to you, even though it seems really strange from this end. So I want to continue talking about, we're still in 11.1, introducing sequences. And the last big idea we had were these limit, well, let's call them limit, well, just the idea of a limit, and then we had this first theorem, which is a pretty big one for us, right? So this theorem down here about if the limit as x goes to infinity of f of x is equal to L, and that function is the same as our sequence for all integers n. I wrote it for n greater than some integer n because it actually doesn't matter if they're different in the beginning. If the sequences eventually match the function, then everything's fine. This is not really going to be an issue for us. Then in any event, when you have that, then the limit of the sequence is the same as the limit of the function, right? So the important part is that the function is equal to the sequence at some point. I'll give a quick example about what happens when it's they don't match in the beginning. So for instance, here, let's do this up on the screen. For instance, suppose I had, and forgive me, I'm still not great with this pen. Let's say I had the sequence a sub n is equal to 1 over n for n greater than 5, right? And maybe I just decide for some reason that a sub 1 is equal to 1,000. This thing is not working great today. A sub 2 is equal to 100. A sub 3 is equal to 5,739. And a sub 4 is equal to -7. All right, so I have these A1 through A4 are just some arbitrary numbers that I picked, but then after that it turns into this sequence 1 over n for n greater than 5. Well, we know the limit as x goes to infinity of 1 over x is equal to 0. And since 1 over x is the same as 1 over n for the integers over 5, oh, I should put or equal to, I started at 5. Then this implies the limit as n goes to infinity of a sub n equals 0, right? The big point there is just that the limit doesn't care about what happens at the beginning. We're talking about what happens when x gets really large. So these first 4 terms being kind of goofy doesn't change what happens as n gets larger and larger and larger, right? Those are the first few terms. I keep finding myself staring at my own picture, which I don't think is narcissism. I think it's my brain just wanting to talk to a person, and since that's my own picture staring me back on the screen, I'm looking at that instead of the camera. I'm trying. Okay, so we want to move on from this. So let's move down. Oops, sorry, I'm still new with these things. So we've got this theorem that we can look at functions to understand the limits of our sequences, which is really convenient because we get all of these limit laws, right? These are very familiar limit laws from section 2.3, I believe, way back in Calc 1, where replace a sub n and b sub n with functions f of x and g of x, and they look very, very similar. So for example, let's go through a few of these. We have the limit of a sum is the sum of limits. That's our first one, or the difference, right? The limit as n goes to infinity of a sub n plus or minus b sub n is the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n, right? You can distribute that limit over an addition of sequences. Same thing with constants. They slide through our limits as we recall. They slide out when we're dealing with functions. This one here, I want to mention, this, of course, does not work when we have something like infinity times 0. In that case, we have to do something different because infinity times 0 is not determined. But otherwise, in all other cases, if it's a constant times 0, a constant times infinity, two constants times each other, then you can take that as your limit. So we might say the limit of a product is a product of limits. Same thing for a quotient, as long as the denominator is not 0. Also being careful if we get infinity over infinity, that also doesn't make sense, right? Remember these limit laws, these work as long as both of these limits exist, and the limit going to infinity is another way of saying the limit does not exist. Here's one. If we have a power on our sequence, we can take the limit of the sequence by itself and then raise that answer to a power. Right, with this little condition here that both of these are positive. The limit of a constant is just a constant, nothing very big there. I want to do an example of this one because it's a little more confusing. If the limit as n goes to infinity of a sub n is equal to L, and f is continuous at L, then the limit as n goes to infinity of f of a sub n is f of L. Okay, so it means if we take a sequence and then we put it into a function, in particular a continuous function, or at least a function that's continuous at the limit of the sequence, then we can just take that limit of the sequence and then apply the function to that value. So let's do an example of this. So last video we looked at the sequence a sub n equals 1 minus 1 over n. I feel like this pad used to work better. Maybe I've been mistreating it. And we determined that the limit as n goes to infinity of 1 minus 1 over n is equal to 1, right? You can look at it and see that those 1 over n terms are getting smaller and smaller and smaller. So you're starting at 1 and subtracting something that's smaller and smaller and smaller. So you get closer and closer to 1. So now suppose I wanted to look at the limit as n goes to infinity of e taken to the power of 1 minus 1 over n. Right? Well, what I'm doing, I'm looking at this function here where f is the function, in this case, f is the function e to the x, and I'm putting in f of a sub n, right? That's what this is right here, e to the a sub n. And what this theorem tells me I can do, I don't have to do any kind of crazy limit thing here and figure out how to do a limit with this exponential. Instead, I can take e to the limit as n goes to infinity of 1 minus 1 over n. Right, so let's down here put it in the language of our theorem. The limit as n goes to infinity of f of a sub n is equal to f of the limit as n goes to infinity of a sub n, which is equal to f of whatever that limit happens to be. That's what our theorem says. Well, what does our limit happen to be? We just determined this. The limit is 1. So this is just e. Okay. So we can often use this when we've got things like square roots, squared functions, really any power functions, logarithms, exponentials, that sort of stuff. Provided their sine and cosine will work as long as those are continuous everywhere. Oh, I should say that this works because the exponential is continuous everywhere, so it's certainly continuous at the limit. So that's our only restriction for doing this, that our function be continuous at the limit. All right, here's another one you will remember from previous courses, the squeeze theorem. You can read through this, but essentially it says if the sequence we're interested in this case is we're trying to figure out the sequence b sub n, and I know that it lives between two other sequences whose limits are the same, then b sub n's limit must also be that, right? It's just, our picture is something like this. If this is my a sub n and c sub n, are two sequences, if I'm graphing them out like this, they're getting closer and closer. If b sub n, let's make it a different color, is something like, is pinned in between these two, right? Whatever their limit is, it's going to have to be the same because it's getting closer and closer to the same thing because it's trapped in between them, okay? So let's, for instance, let's look at another picture of this. There you are. Nope. Ah, there it is. Okay, so here's another sequence I've graphed. This is the sequence. It's got a nice cosine in it. So this is the sequence a sub n is equal to 2 to the negative n cosine of pi n. Okay. Well, if we do a little thinking about this, cosine of pi n, when n is 1, it's the cosine of pi, which is -1. When it's 2 pi, cosine is 1. When it's 3 pi, cosine is -1. 4 pi is 1. So this cosine part is just switching back and forth between -1 and 1. Right? That's all this guy's doing here. So what we're really looking at is a sequence that's trapped between two other sequences. 2 to the negative n. Here, let's write it this way. A sub n is trapped between 2 to the negative n. It can never be any bigger than this because, this can never be bigger than 1. And it'll always be above -2 to the negative n, right? It'll either be equal to one of these or it'll be above this one and below this one. So it's always going to be between these two functions or these two sequences. Well, I can look at, let's see. Oh, stop annotating. Let's look at these two functions, these two sequences as graphs. So instead of looking at 2 to the negative n and -2 to the negative n, I'm looking at 2 to the negative x and -2 to the negative x. And we see that we have these two functions squeezing our sequence together, right? It lives in between them, and so they all go to 0. Okay, so that's what our squeeze function is. Okay, so let me get back to where we're at. Let's go back to our laws. All right. So then finally, the last one, this is really an application of the squeeze function. I will leave that for you to figure out. If you know that the limit of the absolute value of a sequence is 0, then the limit of the sequence itself must be 0, right? A hint is that means you can trap a sub n between the negative and the positive of the absolute value of a sub n, which will both go to 0. So that's how where that one comes from. So these are our nice limit laws. They let us do quite a bit. They make working with limits, if you started to get comfortable with limits previously in this course, then you'll find working with the limits here really nothing new. So let's do a couple of quick examples for the end of this video. So let's see. Let me share my paper. 1 second here. All right. Let's make that a little better. Sorry, I usually set this up ahead of time. I forgot I had moved it. Okay, so what I want to do, I have a few examples we're going to take a look at. Let's look at the sequence a sub n is equal to n to the negative r. where r is some constant. Okay. So our typical route is going to be, say, something like this. Let's consider f of x equals x to the negative r. It's pretty clear that f of n is equal to a sub n for n in the natural numbers, right? So that's just a little symbol to mean n is a member of the set of natural numbers. The natural numbers are just the positive integers. So that satisfies the first part of our theorem, that we have a function that is equal to our sequence on the integers. And we also know the limit as x goes to infinity of x to the negative r is equal to 0 if r is positive. All right, this was something we proved back in Calc 1 for functions, right? As long as r is positive, then this is 1 over x to a power. X gets bigger, the fraction gets smaller. So that means the limit as n goes to infinity of n to the negative r is also equal to 0 if r is greater than 0. All right, so that's a quick application. I should write something like, therefore, that's a quick application of that theorem. And so now we know how to take these kinds of sequences, right? Any sequence that's 1 over n to a power, a positive power, is going to go to 0. Okay. The truth is, and I'm fine with this, we will rarely go through the trouble of rewriting our sequence as a function, showing that it's equal to our sequence on the integers, and then taking the limit of the function and then writing in terms of n. We typically just take the limit in terms of n as if it's a function, shorthanding all of this. I'm going to be fine with that. It is not technically correct. And when I'm working with more complicated things, I seldom do that shortcut. But for most of the stuff we're working with here, it's not going to be an issue. So let's do a couple more examples. So let's look at this sequence. A sub n is equal to 3n over 2n minus 1. Right? And I want to know the limit as this sequence goes to infinity. So let's just see what this limit looks like. Putting in n equals 1, we get 3. When n equals 2, this turns out to be 2. Then we get 9/5, 12/7, 5/3, and on and on and on. Right? So it appears to be getting smaller. Yeah, appears to be getting smaller, but it's not clear exactly what's happening here, right? So let's go ahead and take the limit as n goes to infinity of 3 sub n, or sorry, 3n over 2n minus 1. Technically speaking, what we have to take the limit of is a function like 3x over 2x minus 1, and then show that that function is equal to this on the integers. But it is really just a notational trick at this part. It's not really sensible to take the limit that how we're going to take it in this case, but we do this to shortcut all that extra work. So we can use a variety of methods. I'm going to multiply the top and the bottom of this function by 1 over n. So I get 3 over 2 minus 1 over, oops, I forgot my limit, as n goes to infinity. And then we can apply our limit using the limit laws to the numerator and the denominator. The limit of the constant is just 3. In the denominator, we get another limit of a constant is 2. The limit of 1 over n is 0. So we get 3/2. Okay. So there's actually not a whole lot of new stuff with these limits. This should look very familiar to us from Calc 1, even if that was quite a long time ago. All right, let's do a couple more. We'll do two. Let's do 2 more. All right, let's look at the sequence. B sub n is equal to the natural log of 2n over n squared. This one gets a little more complicated, so I think I am going to write a function, the natural log of 2x equals x squared, clearly. So I'll say let f of x equal this. Clearly, f of n equals b sub n for n in the natural numbers. Okay. Again, that just means n is a member of the set of natural numbers, which are 1, 2, 3, and on and on and on. So let's look at the limit as x goes to infinity of f of x. So the natural log of 2x over x squared. What we might notice is we're getting infinity over infinity. Natural log of 2x as x gets larger goes off to infinity. Natural log of x squared as x gets larger and larger goes off to infinity. So we get infinity over infinity, which means nothing. It's indeterminate. However, we have a nice rule. We can use L'Hopital's here. So I use this little symbol to let myself know what I'm doing. Remember what L'Hopital's rule tells us, that if we have an indeterminate form, something like 0 over 0 or infinity over infinity, we can instead compare the ratio of the derivatives of these two, of the numerator and the denominator. So I'm not doing a quotient rule, I'm taking the derivative of the numerator and the derivative of the denominator separately. So the derivative of the natural log of 2x is 1 over x. There's a chain rule in there, I'll let you work out the details. And the derivative of x squared is 2x. This can be easier written as, can be better written, let's say, as 1 over 2x squared. Well, this, of course, goes to 0, which means, therefore, the limit as n goes to infinity of b sub n equals 0. Okay. Again, we found a function equal to ours on the integers, and we found that the limit of that function is 0, so that must be the limit of our sequence. Okay, applying that rule again. All right, let's do one more example. I think that's all right. You can't see too much of that. I'll try to stay on the left-hand side. Here's another sequence that is a bit different. Okay, so part of the reason I'm throwing this at you right now is when we get towards the end of this chapter, or the end of this chapter, like I told you, we're going to be building these things called Taylor polynomials, and stuff like this shows up. So this is not one of those, I'm just picking a funny, goofy problem to make things tricky. I want to make sure we start getting used to thinking about things like this. So this one, we can't really use that rule. You might not even remember what this symbol n exclamation point is. We call that factorial. And even if you do, you might remember that we don't have any rules about it as far as taking derivatives. So we won't be able to use, about taking limits, right? This is not a function we've done a lot with. So even if we write the function f of x equals x factorial over x to the x, I don't think we have any limit laws that are going to help us. Those both go to infinity as x gets larger, but then we would try to use L'Hopital's rule, but we don't know how to take the derivative of a factorial. So it's not going to work in this case. But let's think about what this thing is. So first of all, let me remind you what n factorial means. This is n times n minus 1 times n minus 2, on and on and on, times 2 times 1, right? So factorial just means you take that integer and you multiply it by every integer lower than it down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. 3 factorial is 3 times 2 times 1 is 6, right? Factorials are really interesting. They show up in surprising places like Taylor polynomials we will get to. They're all over probability theory, something called combinatorics. And they can be tricky to deal with. They grow large very, very quickly, right? 4 factorial is 4 times 3 times 2 times 1 is 24. 5 factorial is 120, right? 6 factorial is 720. So you can see how quickly they are growing. So then in the denominator, we have n to the nth power. Let's just write out a few terms of this to start getting a handle on what this thing does. This is a good idea whenever you encounter something that's unfamiliar. Let's not live just in theory. Let's just write out some terms and see what this thing looks like and start getting an idea of it. So C1 is going to be 1 factorial over 1 to the 1, or 1. C2 is 2 factorial over 2 squared, or 2 times 1 over 2 times 2, right? 2 times itself. 2 times itself twice. Well, yeah. C3 is going to be 3 factorial over 3 cubed, or 3 times 2 times 1, over 3 times 3 times 3. Right. We could, of course, figure these out as numbers, but I'm actually spending more time right now. I want to look for a pattern because I don't care about what these terms are. I want to see if I can find something useful to deal with. Let's do one more because I think we can see the pattern emerging now. 4 factorial over 4 to the 4th is 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. Okay. So let's try to write out a general term. I mean, we already have the general term C sub n is this, but I see something happening here that we might be able to rewrite this now a little bit better. So n factorial over n to the n is n times n minus 1 times n minus 2 dot 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 times 2 times 1, right? Depending on how high we go. And all of this is over n times n times n times n times n. Now, let's, oh wait, sorry. There needs to be an ellipsis in there. I don't know why I wrote it in such weird spacing, but let's do a couple of things. First of all, notice in the top, n factorial, there are going to be exactly n factors. 1, 2, 3, just counting up to n. Each of those numbers will get multiplied. In the denominator, there are n factors because we're going to the nth power, n factors of n, okay? So there's the same number of factors in the denominator as there are in the numerator. Let's look at these factors. First of all, we've got an n over n, so we can just get rid of that. Then we'll have n minus 1 over n minus 2 over n, and on down, over n, right? I can take each factor in the top and couple it with a factor in the bottom and separate those fractions, right? For instance, in this one up here, this is 2 over 2 times 1 over 2. This is 3 over 3 times 2 over 3 times 1 over 3. This is 4 over 4 times 3 over 4 times 2 over 4 times 1 over 4, right? So in all these cases, we get a 1 in front. We get a 1 in front, and then we're just multiplying it by all of these numbers that are each smaller than 1. Okay. And at the end, we have a 1 over n. Okay. So all of these numbers here are less than 1, and we're multiplying them by 1 over n. What does that mean? Well, I can say C sub n has got to be less than or equal to 1 over n. If you take something like 1 over n and you multiply it by things that are all less than 1, you get something smaller. To be clear, this works because everything's positive, right? I didn't say that explicitly, but we're talking about integers, everything's positive. So what that means, C sub n is stuck between 0 and 1 over n? Well, also, the limit as n goes to infinity of 0 is 0. The limit as n goes to infinity of 1 over n is 0. So we've got our sequence stuck between two sequences whose limits are 0. The squeeze theorem tells us that the limit as n goes to infinity of c sub n is equal to 0. Okay, so that one took a little bit of poking around at. And like if you were in my classes previously, we're getting further and further into math. There's a lot more poking around and a lot less just follow these instructions. So I think, yeah, that will be it for for this section of that chapter. I think there's one more little section I'll do on some odds and ends, although we may have covered everything. Maybe I'll just cover them in some examples. Anyways, see you next time.